All right, so we just learned about the force on moving charged particles. And so today we're going to focus on the force on a current carrying wire. The book starts off the section kind of oddly, I think, and introduces the magnetic field produced by a current carrying wire. And the reason I say it's kind of odd is because the entire next chapter, chapter 12, is dedicated to sources of magnetic fields. So we're just going to mention this briefly, and then it's going to show up on the video for Friday. So here we've got a current carrying wire. The current is in the picture traveling up the page. And so if you want to know the qualitatively the magnetic field that's produced by this current carrying wire, you simply point your thumb in the direction of the current, and then you wrap your hand or your fingers around the wire. So this is using the right hand, like all of our right hand rules. So thumb in the direction of the current, wrap your fingers around your fingers as you wrap around or curl around the wire. Your fingers point in the direction of the magnetic field. And so in the plane of the paper, in this next picture, in the plane of the paper, on the left-hand side of the wire, the B field is coming out of the page. On the right-hand side, it's coming in. And so if you put that all together, here's what the magnetic field looks like that's generated from a current carrying wire. And like I said, we'll come back to this in the next video for chapter 12. So the reason that it's out of place is that really it seems like most of chapter 11 is focused on what happens to charges that are moving through magnetic fields, and we're not really interested yet in how those magnetic fields get generated, right? And so this next section, the force on a current carrying wire, this is if there's a B field, what happens to your current carrying wire if it's placed in that B field. So first off, from the last video, if we've got a charge Q moving through a B field, the force on that charge is QV cross B. And I think the most obvious question now that we're moving to a current carrying wire is, what about if we've got a lot of charges, right? Or a continuous stream of charges, the idea of a current. So recall that the current is defined through this expression, and the number of charge carriers, or the charge carrier density. E is the charge itself, A is the cross-sectional area, and V is the drift speed or the drift velocity. So if we check out my picture here, I've got a wire in a B field. So the B field is up in this picture, and my current carrying wire, the current is traveling to the right. And we want to consider the force on all the charges, right, in the wire. So the way we're going to do this is we're going to break the wire up into tiny chunks, that little DL that I've got highlighted here. We're going to break up the wire into little chunks and think about, all right, well, how much force, right, is on that little chunk? And we're going to call that DF. And then eventually what we're going to do is we're going to integrate over the entire wire. All right, so how much force is on that little chunk? Well, it's whatever the Q there is multiplied by V cross B. And whatever the Q is there is the first part of that expression. It's the charge density, or the particle density, the charge, the area, and then all multiplied by dl. And so you can see the units work out there. N has units of per meter cubed, and then ADL has units of meters cubed. And so those units will cancel, and we'll just be left with the unit of E, which is the charge. And so so we can rearrange that expression because DL and V are actually pointing in the same direction. Because we've got a current carrying wire, the charges are moving along or through the wire. And so all I've done here is I've swapped out I've swapped DL and V and DL. And so since those vectors point in the same direction, right, it doesn't matter which one gets crossed into the B vector. And so this right here is exactly the definition for current. And so we can rewrite the entire expression as the little chunk of wire has this force dF I dl cross B. And so if you integrate over the entire wire, or the full length, then you get this expression down here. That the force on a long straight current carrying wire of length L is I L cross B. And so exactly analogous to Q V cross B. So this is the force on a length of wire L that's carrying a current I in a magnetic field B. One of the most common applications of magnetic force on current carrying wires is the idea of a motor. And a motor is essentially a way to convert electromagnetic energy and convert that into mechanical energy. And so this comes about when you have basically a loop of current placed in a magnetic field. And so we're going to introduce the idea of the torque generated on a loop of current with the introduction of a motor. So here I've got a diagram of a motor, which a simple motor, so I've got a loop of wire placed in a magnetic field, and that loop of wire is hooked up to a circuit. And so the idea in the picture here is we've got a magnetic field in this direction, so there's our B field, and then we have current in the wire. According to this setup, we have current going in that direction. And so thinking about our direction of current and our direction of the magnetic field, then on this side over here, this portion of the wire, this portion over here, we're going to get a magnetic force downward due to the direction of the motion of the charged particles and the B field. And in this segment, we're going to get a force up. So on the left side of the loop, the force is down, the right side, the force is up. That's going to cause rotation about this center axis. Now, the force on this portion, well, at this exact moment, the force would be 0 because that current is parallel to the magnetic field. But you can imagine as it rotates, that'll no longer be completely parallel. And so that force, if let's say it rotates 90 degrees, then the current is vertical, the magnetic field is horizontal, and so that, let's see, what direction would that be? That magnetic force would be in this direction. Let's see if we can draw it like into the middle of the loop. But then you've got this portion over here that has a force towards the middle of the loop. And so those two forces essentially cancel out and don't contribute anything to the rotation. It's the forces on these two ends of the loop that are generating the net torque that the loop experiences. And the way that the simple motor works is that there's this segment here where the loop connects to sort of like the driving circuit, where this curved shaped piece is called the commutator, and these pieces here are known as the brushes. And basically what happens is this loop rotates until the commutator, those gaps there, line up with the brush, and then there's no longer a connection with the circuit, And so the loop continues to rotate because there's no net torque on the loop anymore, so it continues to rotate essentially at the speed at which it was rotating until the connection gets made again and a net torque is generated and it continues to accelerate or spin again. And so what happens is you get this continuous rotation of the loop in the magnetic field, essentially generating your desired effect. So we're going to look at our loop here, and we're going to look at it sort of from the side. So now we're sort of tilting that view that we were just looking at. So we've got our magnetic field pointing from left to right, and we've got our loop of wire, and we want to investigate the torque that the loop is experiencing being placed in this magnetic field. And so if you can see what's going on here, I've got my wire, and then this is kind of like a cross section, so the top part shows that the current is going into the page, and the bottom part here is showing the current coming out of the page. And then I've drawn the normal vector here along this line. So that is the, remember if we're thinking about the area vector, that normal vector is the direction that's perpendicular to the area vector, or perpendicular to the surface of the loop. It's the direction of the area vector, excuse me. So the torque then on the loop is this expression right here. This is essentially coming about from the force being I/L cross B, and the A here is the area of the loop. And so we can define something called the magnetic dipole moment, and this is the magnetic dipole moment is something that's defined for any loop of wire, and the magnetic dipole moment is defined as the current through the loop multiplied by the area of the loop. And then it's a vector, so the direction of the magnetic dipole moment is the direction of the A vector. It's perpendicular to the loop. And so if we use that definition for the magnetic dipole moment, then you can rewrite the torque on your loop of wire in a magnetic field as torque is the dipole moment mu crossed into the magnetic field. And relatedly, you can also talk about the potential energy that's associated with your loop being placed in a magnetic field, and that's mu dotted into the B field. Now I will note that over here, for a current loop in our magnetic field, the net force is 0. And that's kind of easy to see because for a loop, you're going to have some charges traveling this way in your magnetic field, but then you've got charges traveling this way in your magnetic field, and so the net force there is 0. Of course, the net torque is non-zero, and that's what we pointed out down here. Now, actually, just one last thing. So, since the magnetic force on moving charged particles is perpendicular to the direction of their motion, the magnetic force does no work. So, you may be looking at this motor and wondering, or you may be looking at it and thinking, all right, the magnetic field is what's essentially doing the work that's creating the motion here, or the change in the motion of this loop. And that's actually not correct. I think the easier way to think about this is if we disconnect the circuit, so let's just break the circuit here. So if we break that circuit, we would have a current carrying wire or excuse me, we would have a loop of wire with no current in it placed in a B field. And of course, there would be no magnetic force because there's no movement of charge. And so you can think of what's driving this change in the motion is not actually the magnetic field, but it's actually the fact that the charges are moving. And what is making the charges move? Well, it's the presence of the battery, right? So when I put that circuit back together, now all of a sudden charges are moving, and that's what's responsible for the change in energy or for the work that's being done. Remember, that battery is doing work per unit charge, and so that's what's giving rise to the change in rotation of the loop. Another interesting thing that magnetic force allows us to determine is it allows us to determine the charge carrier inside a conductor. And this is essentially referred to or known as the Hall effect. And you can remember when we introduced circuits and we introduced the idea of current, we said it was completely arbitrary in our analysis whether it was positive charges moving to the left or negative charges moving to the right. Our circuit analysis remains the same and is consistent regardless of which of those stories is the reality. And so so it turns out that if you have your charges moving in a magnetic field, then you can actually determine which charge carrier is responsible for the current. And let me just show you how that plays out. So I've got essentially our two pictures of what current could be. I've got a conductor here, and I've got a current going from right to left. So this is the case in both pictures. Current is in that direction. In the left picture, though, the charge carrier, that's the mobile charge, is the negative charge, and so that's a charge moving to the right. Well, if this conductor is placed in a B field as shown, then those charges that are moving to the right and are negative, there will be a magnetic force on those charges. Oops. There will be a magnetic force on those charges in the downward direction. And so negative charge will build up on this part of the conductor. And that means that positive charge will build up on this side of the conductor. And if there's a separation of charge there, then there's essentially a potential difference, and an electric field will get set up. And that electric field will point from the top to the bottom. And so there's a magnetic force down. Well, as that electric field gets set up, well, now there's an electric force in the upward direction, right? Because these are negative charges. And you could imagine at some point that magnetic force down and that electric force up would be the same magnitude, and then essentially you would reach some equilibrium there where the charges just move through undeflected. The point of the Hall effect is that if you can measure the potential across the top and the bottom of the conductor, in this case, you will determine that the top, right, is at a higher potential than the bottom. But then over here in this left picture, again, the current is defined going from right to left. So here's our positive charge moving to the left. That means we've got a magnetic force down, and so the positive charges will accumulate on the bottom. The negative charges will accumulate on the top. That'll set up an electric field in the upward direction, and so that'll set up an electric force on the positive charges in the upward direction. And so if you measure the potential difference across this conductor, you would get that the bottom is at a higher potential than the top. And so if you run this experiment and measure the potential across the top and the bottom, you can immediately determine if it's the positive charges that are moving or the negative charges that are moving. And of course, When you do that, for most conductors, you find that it's the negative charges that are moving. But there are some materials, tungsten being one of them, that the positive charges are actually the charges that are mobile. And it's a little beyond the scope of the course to get into the details of that, but just understand that it is possible. There is a mechanism or a method that can be used to determine whether it's the positive charges or the negative charges that are circulating in a conductor. And so, right, the Hall effect allows us to answer that question. The Hall effect in that discussion also allows us to introduce something known as a velocity selector, and that's a very useful technique that gets used a lot in instrumentation and in labs. So here's my picture, running out of room here. I've got a B field pointing into the page, and I've got an electric field. So there's my B field, and then I've got an electric field pointing down. And I've got a positively charged particle traveling to the right. And so if I do force analysis with this charge, right, the net force in the y direction, if my y direction is the up-down direction, the net force in that direction would be the sum of the forces of the magnetic force. So right-hand rule, the magnetic force is going to be up, so I've got a plus QVB. And there's no sine theta because theta here is 90 degrees. And then the electric force is down, so minus QE, and that's all got to equal MA. And if the acceleration is 0, that is, if this particle just travels straight through, then the requirement for that to happen is that the speed at which the particle needs to be moving is the ratio of the electric field magnitude divided by the magnetic field magnitude. And this is why this is called a velocity selector. So if you shoot a bunch of particles through this region where there's a perpendicular electric and magnetic fields, then only charges that have the specific speed that's equal to the ratio of the magnitude of the E and B fields, only those particles will end up going through undeflected. And so what that means is if you're shooting these particles through, right, so let's try to do this here. If you're shooting these through, it's only particles with the right speed that'll come out the other side. And so let's say you've got a little detector over here. It's only particles with that specific speed that'll make it through the field and pass into that detector. And any particle that's charged and moving at a different speed will get deflected and miss. So let's say the magnetic force was, let's say the electric force is a little larger than the magnetic force, then that means as we enter, right, this thing's going to start deflecting down that way because there will be a net force in the downward direction. And so it will miss the detector or the window there. And so only charges that are moving at the exact speed of, that is the ratio of the magnitudes of the E and the B field, make it through. And again, this is known as a velocity selector, and it shows up in a variety of different lab and instrumentation settings.